What if a computer could try every possible answer at the same time? Not faster, simultaneously. That's not science fiction. That's how quantum computers actually work. Ever look at your phone or laptop and think, this is amazing, but what's next? What's the next giant leap in computing? Well, get ready, because we're about to dive into the mind-bending world of quantum computers. And I promise, by the end of this, you'll understand the basics of how these incredible machines actually work. First, let's talk about the computer you're using right now. It works on a simple principle: bits. A bit is like a light switch. It can either be on or off, a 1 or a 0. All the amazing things your computer does, from streaming this video to sending emails, are all just incredibly long sequences of these ones and zeros. It's a binary system, clear and definite. Quantum computers, however, play by a completely different set of rules, the rules of quantum mechanics. Instead of bits, they use something called qubits. Now, this is where it gets cool. A qubit isn't just an on or an off. It can be a 1, a 0, or, thanks to a principle called superposition, it can be both a 1 and a 0 at the exact same time. Imagine spinning a coin. While it's spinning, it's not heads and it's not tails. It's in a state of both possibilities. Only when it lands, when we measure it, does it settle into a definite state of either heads or tails. A qubit is like that spinning coin. It exists in a cloud of probabilities until we look at it. This ability to be in multiple states at once is what gives quantum computers their incredible power. While a classical computer with 3 bits can only represent 1 of 8 possible combinations at any given time, a quantum computer with 3 qubits can represent all 8 combinations simultaneously. As you add more qubits, the power grows exponentially. With just 300 qubits, a quantum computer could represent more states than there are atoms in the entire known universe. Now, how do we actually make these qubits? Scientists are experimenting with a few different methods. One popular way is using tiny particles like electrons. Electrons have a property called spin, which can be either spin up or spin down. Think of it like a tiny spinning magnetic arrow. By using carefully controlled microwave pulses, scientists can nudge this electron spin into a state of superposition, where it's both spin up and spin down at the same time. Another method involves using tiny superconducting circuits. When cooled to temperatures colder than deep space, these circuits start to exhibit quantum behaviors, and we can use them to create and control qubits. So we have these qubits in a state of superposition. What's next? This brings us to the second magical ingredient of quantum computing: entanglement. Albert Einstein famously called it spooky action at a distance. Entanglement is when you link 2 or more qubits together in a special way. Once entangled, their fates are intertwined. No matter how far apart you separate them, if you measure the state of one qubit, you instantly know the state of the other. It's like having a pair of those spinning coins. If you know one landed on heads, you instantly know the other has to be tails, even if it's on the other side of the galaxy. This connection allows information to be shared between qubits in a way that's impossible in classical computing. By combining superposition and entanglement, quantum computers can explore a vast number of possibilities all at once. This is the core of a quantum algorithm. Instead of checking each possibility one by one like a classical computer, a quantum computer navigates this huge space of solutions simultaneously. Kind of like being able to check every book in a giant library at the same time to find a specific sentence. But there's a huge challenge. Qubits are incredibly fragile. The slightest vibration, a stray magnetic field, or even a tiny change in temperature can knock them out of their delicate quantum state. This is called decoherence. It's like trying to keep that coin spinning forever. Eventually, it's going to wobble and fall. To combat this, quantum computers have to be kept in extremely controlled environments. We're talking about massive sci-fi-looking refrigerators that cool the quantum chip down to near absolute zero, colder than outer space, and they're shielded from all external interference. This is why you won't be buying a quantum laptop anytime soon. These machines are massive, expensive, and require a whole team of scientists to operate. So, what are these powerful, fragile machines good for? They're not going to replace your laptop for browsing the web or playing games. Classical computers are actually better at those tasks. Quantum computers are specialized tools designed to solve specific, incredibly hard problems. One of the most famous examples is in drug discovery and material science. Simulating how molecules interact is a massively complex problem for even the most powerful supercomputers today. But because molecules themselves are quantum systems, a quantum computer is perfectly suited to simulate them accurately. This could let us design new medicines, create more efficient batteries, or develop revolutionary new materials, all in a fraction of the time it would take now. Another huge area is optimization. Think about a delivery company trying to find the most efficient route for all its trucks. As you add more and more stops, the number of possible routes explodes. A quantum computer could evaluate all these routes at once to find the absolute best one, saving massive amounts of time and fuel. This applies to financial modeling, logistics, and even improving artificial intelligence and machine learning algorithms. And of course, there's cryptography. Many of the encryption methods we use today to protect our data rely on the fact that it's incredibly difficult for classical computers to factor large numbers. A large-scale quantum computer, using an algorithm called Shor's algorithm, could theoretically break this encryption easily. This is a big reason why governments and companies are racing to develop quantum computing, and also why scientists are already working on new quantum-safe encryption methods. We're still in the very early days of quantum computing. It's like the 1950s for classical computers when they were room-sized machines used only for a few specialists. But the progress is incredibly fast. We're moving from having just a few noisy, unstable qubits to having machines with hundreds of them. As the technology matures, we'll be able to solve problems that were once thought to be permanently beyond our reach. So, to recap, classical computers use bits, which are either on or off. Quantum computers use qubits, which can be on, off, or both at the same time, thanks to superposition. These qubits can be linked together through entanglement, allowing them to perform massive parallel calculations. They are extremely sensitive and need to be kept in super cold and isolated environments to work. And they're designed not to replace our current computers, but to tackle specific, monumental challenges in science, medicine, and technology. The journey into the quantum realm is just beginning, and it promises to reshape our world in ways we can only start to imagine. It's complex, it's a little strange, but it's the future of computation. Thanks for joining me on this deep dive. If you enjoyed this and want to learn more about the amazing future of technology, make sure to like this video and subscribe to the channel. Let me know in the comments what other mind-bending topics you'd like me to explore next. See ya in the next one.